This is Mark D'Antonio with Sky Tour Radio, coming to you tonight with my wonderful co-host Amanda Curran. Hello there, Amanda, and how are you?
Hi, Mark. I'm well. How are you?
Just fine. And we have our special guest and return guest to our show who will be with us for the evening, Daryl Mason. Welcome, Daryl. How are you doing?
Hi, Mark. Hi, Amanda. Thank you for having me. I'm doing well. I hope you are also.
We are doing fine, thank you. And Daryl's going to be here possibly more frequently as time moves on. We're going to kind of leave it up to him, but he does wonders for us. He's a really good guy, knows an awful lot about astronomy, and it's actually fun to bounce things off of him, and as well as Amanda. So it's interesting because Daryl knows a lot about astronomy. Amanda's learning about astronomy. And so between the three of us, the happy triumvirate, we're actually able to bring astronomy to the masses in a way that everybody can understand. And that's something that's very important. Now, I want to just welcome the greatest listeners on the planet, the KGRA listeners, to our broadcast. And I would also encourage you to subscribe to a companion stream to Sky Tour Radio. It's called Sky Tour Live Stream. And we visit the deep sky every single clear night we can. And we show you the deep sky objects for the constellations that are up at the moment. And we have a good time viewing them. We talk about them. We explain what's going on. We show you oddities in the universe that are just amazing. So hopefully you'll join us for that. We've had some really interesting live streams lately. When we streamed the lunar eclipse a couple weeks ago, we actually caught a meteor hitting the moon. It was outrageous. It was beautiful. It was a little flash, bam, that we saw in the lower left of the lunar quadrant there. And this was actually while the moon was a deep red. It was beautiful. So, that's Sky Tour live stream. We can see those things, and we see many oddities. We see satellites moving through the field and so forth, which is really interesting, especially if you haven't seen them before. And then you see them moving through the field. You go, wow, what is that bright thing that just went through the field? Well, it was a satellite. And then you learn how these satellites go through the field. We actually look for satellites in the sky. We even find geostationary satellites, the ones that are just hovering over the same spot on the Earth. So join us at Sky Tour live stream and enjoy the universe as never before. Now, if you're interested in getting something or purchasing something, you can get some really cool 3D printed Moon, Mars, and Pluto craters and landscapes that we print here in our visual effects shop. And these are taken directly from the NASA space probe data. And if any of you have questions, you can submit them to us at skytourradio@kgraradio.com. And lastly, don't forget, subscribe to this channel, which is the place where the Sky Tour News that's created by Amanda is placed. And her YouTube channel is DannyFan1. That's DHANIFAN numeral 1. All right, DannyFan1. And she provides the news of space for our broadcasting week. So, all that said, I'm done talking. So I just throw it over to everybody else. No, I'm just kidding. Tonight on Sky Tour Radio, we're going to talk about.
Sorry, I'm laughing. Mark, can I jump in for a second?
Please do.
I want to give Amanda a great big pat on the back. She caught one, actually possibly two sats the other night that everybody else missed. So yay for Amanda.
Oh, thank you.
Also, last night was a great stream. You got some great images, and I hope you will share that one of Thor's helmet with me once you get it processed. I don't do Facebook, so I have to ask Mark to send me what he makes. But it was just a beautiful night last night.
It really was. Last night, once in a while, folks, we get this beautiful night, and Sky Tour live stream, I see a clear sky, and I don't care what I'm doing. I don't care what I have planned for the night. I'm supposed to be going to a movie with my family? No, it's clear. I'm going to be doing streaming. I cannot sit in a movie theater in the dark watching a movie when I know it's clear out and dark. All right, because it could be that magic night. Last night was one of those magic nights. It was beautiful. And the only reason that I had to basically shut down was, as it turned out, the dome interfered with our last photo that we were taking, and that's okay. But the only reason we typically, will have to shut down is because clouds came in. And that's what happened last night, but it was later. And so when that happened, I actually had a little bit of relief. I said, okay, I can't stream anymore. I'm forced to shut down the observatory. And that's what we do. Now, the Sky Tour Livestream Observatory is known as the John Zach Memorial Observatory because my friend John and I were creating this observatory. And of course, John ended up dying. And I put everything aside probably a good 4 or 5 years. And then finally, after I had my surgery and was trying to recover from that, I had to learn how to walk again and talk again. I mean, it was a disaster. But after that all happened, I decided, you know what? As part of my therapy, part of getting better, I'm actually going to build this observatory and I'm going to make this work. Yes, and I did. I made it a fully automated system, except for the movement of the dome. But as I tell people in the stream, I show them the motors. They're sitting right next to me. They're in my face all the time because I'm actually going to implement a system to rotate the dome automatically. The idea is to get all of it working here where we are in northwestern Connecticut and then move it in its entirety out to Arizona under a nice dark sky. And I actually have friends out there that are offering up their land to put it on. It's like, wow, it's like, I want to actually have a plot of land to put this on, but they're saying, well, you can put it here. And there's a few people in the stream that are saying, well, I can manage it for you. I live nearby. I'll come manage it. So there's people that are actually willing to do that too. So we're on our way. And SkyTour Livestream is actually becoming a little bit more formalized, and the idea at the end is we're going to be able to take and bring to the world this deep sky astronomy from a really, truly deep sky. Right now, we have a little bit of light pollution here in Connecticut, but we're in an area that thankfully doesn't have as much as some areas have. But it has more than some other areas have. But we'll see. We're getting there. Now, in tonight's show, we're going to actually be focusing on one of the main constellations, actually, that you see in the evening sky in February. And that's the constellation of, who knows? Amanda or Daryl? What would you say is that one of the main figurehead constellations of the winter sky that we just love to talk about?
Orion.
You got it. Yeah, that's right. I think both of you were thinking Orion. And what's funny about Orion is, okay, it has been one of my favorite constellations. And Orion is also the middle name of my youngest son. His name is Hunter Orion. And the two names, Hunter and Orion, because Orion is the hunter in mythology, the Orion part of his middle name happened by chance. We had decided his name was going to be Hunter. And then my niece walked into the house, not knowing that, because we had just decided. And she says, I wanted his name to be Orion, actually. And of course, I got really crazy looks from my family who were saying, are you nuts? You're going to give your kid the name Orion? What's wrong with you? At the same time, that's when my niece walked in and said, hey, Uncle Mark, you gotta name your kid Hunter. And we all looked at each other and said, wow, Hunter Orion. I mean, it was destiny. So he became Hunter Orion D'Antonio. And my oldest son was already Gabriel, and his middle name is Galileo. Because Galileo is one of my favorite, most tenacious seekers of truth, I think, in world history. And I think that Galileo, for all his warts that he had in his life, Galileo was actually a brilliant scientist who made some discoveries that changed the face of history. So my kids have these names. I mean, you could expect that from me, though, because I had two dogs before that. Not comparing them to the kids, of course, but two greyhound dogs. And they were named Tycho and Kepler, which were, of course, competing astronomers at the time when they were both alive. And so these dogs were kind of always at each other's throats and kind of nemesis to each other. So it was natural that one be Tycho and one be Kepler. So it stuck. Anyway, moving forward into the show, I just want to say, tonight, as we talk about Orion, we're going to make this show all things Orion. Okay, all things Orion. We're going to talk about the galaxy, why Orion's so bright. We're going to talk about the stars in Orion. And then we're going to discuss things like the Orion Nebula and what that means, what it is, and so forth. But we're also going to talk about, we're going to have an exoplanet roundup, actually. We do an exoplanet roundup each week, mostly. And we talk about exoplanets of interest. Well, this week, we're going to talk about exoplanets in the Orion Nebula, because there have been exoplanets that have been found in the Orion Nebula. In fact, 10 times as many objects have been found in the Orion Nebula as previously, more than previously thought. So it really is amazing. So here's how it works. Now, the Orion Nebula is about 1,400 light years from the planet. And what is the nebula? Well, nebula means cloud. And it's a cloud of gas and dust. But we see this gas. How can we see gas? Gas is transparent. Well, this particular gas is hydrogen gas. And the hydrogen gas is gas that has been ionized by bright stars, hot ultraviolet stars. So this is something that is very interesting, because hydrogen has one proton and it has one electron. That's the hydrogen atom. Simplest form of atom that there is. All right. And in the beginning of the universe, there were only nuclei, only protons. All right. The electrons came actually later, and then they combined with each other later on. We talked about the origins and so forth, how that happened, but suffice it to say that the simple hydrogen atom has an electron cloud. We don't say electrons are particles. They're like clouds. They're everywhere at once. And that's a mental and a brain freeze coming, because when you try to say that electrons are everywhere at once, the human mind can't comprehend what that means. All right. But it's true. And we speak of things called the Heisenberg uncertainty principle. We talk about how the Bohr model of the atom, BOHR, Niels Bohr's model of the atom, doesn't really work with atomic structure so much when we talk about electrons. But that all said, this electron cloud that's in the hydrogen atom can be an absorber of energy. So if ultraviolet energy comes in from another source, like another bright star, that electron jumps wildly. That cloud jumps wildly and gets so far away from the atom that it's effectively not attached to the atom anymore. It becomes a free electron, right? And that free electron now is free to just float around, but it undergoes collisions rather. They actually will combine again with other hydrogen atoms. So if an electron has a spot to go in an atom, it'll tend to go into the atom again. This is called recombination. And once the electron loses some energy from bouncing around off the atom, it'll recombine. And as it recombines, it goes to a specific energy slot, okay, an energy level, we call it, inside the atom. And when it does, that electron will cause the atom to give off a very characteristic red light. And when you look at some of these nebulae out there, you'll see that they glow in this red light. And that red light is the light of what is known as hydrogen alpha. And it's a certain frequency that will always happen when you get this recombining electron going back to the hydrogen nucleus, all right, to make it an atom again. Because it drops right back in and goes to a specific place every time. And that is what we call that transition, that energy transition that gives off this red light. Very characteristic. We see it in the same place in the spectrum when we look at a spectrum of a nebula that's giving off light like this. And it's a well-known process. Now, we also call this, the ionized hydrogen region. That's why it's called sometimes H2. That's Roman numeral 2. Well, you would say, well, why isn't it called H1? Because it only has one electron. Why the two? That's confusing. Yes, I agree. Except H1, H Roman numeral 1, is the base state of the atom. It's the state of the atom where it has a proton and an electron. And when the electron leaves the atom, then it is H2. It's an ionized hydrogen, and that's why the H Roman numeral 2. So these regions are also called H2 regions. Roman numeral 2, H2 regions. All right. So we also know them as stellar nurseries. These are places where stars are born. Why is that? Well, because the hydrogen that is ever present in the universe, in fact, hydrogen is the most full element in the entire, right? In fact, it's all there was besides a few other trace elements in the beginning until large massive stars were born, created more elements in their cores, and exploded in supernovae. Then new stars were formed from those elements, all right, that had those elements in the interstellar medium. And it went on and on and on until now stars like our sun were formed, and the stars like the sun has things like it has all kinds of elements in it, all right, in the atmosphere of the sun. And the atmosphere is the outer envelope of hydrogen gas that's too far away from the core to fuse, all right? But the center of the star has a lot of hydrogen in it, which is still fusing into helium, right? So the star is like a hydrogen reservoir, and the core has the hydrogen temperatures and then rather of the hydrogen and so forth and the pressures to undergo fusion. This is basically how the stars work, all right? And as a star goes through its evolution, then those elements that are mixed in with the hydrogen in the outer parts of the star may come down and get subsumed into the core. And if the star is massive enough, then other elements can be made from those, all right? Or if a star is not massive enough, then there's other processes that can go toward making other elements. One is called the S process. It's something where neutrons are added to atoms, and those neutrons can become protons under certain conditions. And so we get heavier elements down the periodic table because as the protons increase, so does the atomic mass, and it becomes a new element, all right? And that's how we get new elements, all right? So we get them in a variety of ways. Supernovae cause elements to be created, as we've talked about before. And then this S process, which is the neutron capture, it's called, followed by the conversion to a proton to make a heavier element. This also happens in stars that are about as massive as the sun. So all stars can make new elements in a sense. So once they finish their lives and they blow out their outer shells to the universe or explode in a supernovae, depending on their mass, then new stars form from all of that. And that's kind of where we are. The Earth and the Sun formed 4.6 billion years ago. But that was 9 billion years plus after all the rest of the universe had been created. So that's over 9 billion years into the creation of the universe. So we had a lot of excess stuff floating around. All right. So this is interesting. The Orion Nebula, in fact, is at that position. Right? It's 1,400 light years away, as I said. It's a stellar nursery with lots of dark dust in the cloud, lots of gas in the cloud. It has hydrogen. There's some helium floating around, and there's some other stuff in the cloud that are floating around. And also within this nebula are these dark nebulae that are actually dust. And these dark dust clouds are coalescing. They're actually self-gravitating and forming more dense and dense clouds within them. And they go by various names. We've talked about them on the Sky Tour live stream as Bach globules. These are named for Bart Bach, who was an astronomer, a famous astronomer, who was actually one of my professors. And Bart Bach was the man who discovered these Bach globules and what they mean to star formation and possibly star system formation with planets, right? So they're also known as proplyds, and that's Proplyds, proplyds. And so we would see that, and we do see in the Orion Nebula that there's a lot of these in the Orion Nebula. So there's a lot of places in the nebula where stars are forming, where possibly star systems are forming. And it turns out that whereas we thought there was a certain rate of these forming in the Orion Nebula, it's 10 times higher than we ever thought. This is recent research. Now that means that we're also going to find a lot of what are called brown dwarfs. What are brown dwarfs? Amanda, you may know them, but we've talked about these before, and I'm not going to ask Daryl the question. He knows the answer, but I want to see if Amanda knows, because we've talked about it, and I just want to see if she remembers. I know I'm putting you on the spot, but do you remember what a brown dwarf is, Amanda?
A brown dwarf?
Brown dwarf.
I'm not sure what a brown dwarf is, because I thought a white dwarf was when a star collapsed in on itself.
That's the remains of a star like our sun after it dies. That's correct. But a brown dwarf.
Okay, so a brown dwarf is.
Brown dwarf is actually a. You want to talk? Okay, sure. Daryl, go ahead.
Okay. Well, Amanda, a brown dwarf is, you might call it a failed star. You take a whole lot of mass like Jupiter. In fact, you take a bunch of Jupiters and you cram it all together, and there is tons of mass, tons of heat, tons of compression, but it is not quite enough to ignite the star. So it's just a big old brown lump of gas floating out there in space. Compressed gas. Imagine a super Jupiter. Uh, if it had, well, what is it? Mark would say 70 or 80 times its.
About 80 times its mass, yes, Daryl.
Yeah. Now, if it was 80 times its current mass, it would ignite and become a star. It would undergo nuclear fusion and become a star. Brown dwarfs, they're great big, but they're not quite that 80 mass point, so they do not ignite fusion. And they're just big, warm, brown lumps of compressed gas out in space.
Yep. That's right. Yeah, thank you, Daryl. That's a good way to put it. Big, giant, compressed brown lumps. I like it.
Yeah.
It's actually true, though. He's right, folks. It is basically, and they are warm. They actually can be pretty hot, actually. Brown dwarfs, left alone in space, would glow red hot. You'd see them glowing red. All right, but they wouldn't be hot enough to start that fusion reaction that Daryl's talking about. We need to get up to somewhere around 13 million degrees to start fusion of elements. So I think that I shouldn't say 13. It's like, I think it's 13 million Kelvin, actually. And we're going to talk about temperatures at some point, so you understand there's a Kelvin temperature scale, there's centigrade or Celsius temperature scale, and of course the Fahrenheit scale that we're so used to using. We should just go to all one and just be done with it. And then let people just convert in their heads for a while, and then finally they'll figure it out. In astronomy, we talk about Kelvin, but when we talk about temperature, we don't say degrees Kelvin, we just say Kelvin, all right, or kelvins, like it's like the surface of the sun. Yeah, you can measure in kelvins, okay, but in terms of temperature, it's a certain temperature of degrees, you see. So we have to just straighten all that out at some point, just to make sure everybody understands. But and the concept of a failed star, we hear that a lot, and Daryl's right. They call it a failed star. They call a brown dwarf a failed star. But
I have a question.
Okay, go ahead.
Is a brown star forever doomed to remain a brown star? Is there anything that could happen that could add more mass to make it a white dwarf, or?
Well, not a white dwarf. See, the thing about, you don't say.
Or a star. A star.
Yeah. It would probably form an M star, a dim red star, if it did accrete enough more mass.
Yeah, it would actually have to accrete, quite a bit of mass.
Could it lose more mass, and then what would happen?
Well, if it lost more mass, then it would just become less of a brown dwarf, and just more of a hydrogen ball that's less than hot. It would become some of that would end up dissipating over time. So for sure, but still, no. The brown dwarf is an oddity. They were first discussed some years ago, and I guess we knew about brown dwarfs back when I was getting my degree, but we didn't actually spend too much time talking about them because we're basically in a mode where we're just trying to figure out what was going on, wherever it was going on.
I dare say the prevalence of infrared space observatories now has probably helped find a ton of brown dwarfs.
Oh yes, it definitely has. And what Daryl's referring to, just in case you don't know, some of you do. In fact, I would dare say a great many of you do, is that infrared energy, of course, is heat, and we always look for residual heat around stars or so forth. And for instance, well, let's talk about Betelgeuse. Okay, Alpha Orionis, the brightest star in Orion. Alpha Orionis actually has a huge amount of residual infrared energy emanating from all around it. This is how we've discovered that Betelgeuse, the brightest star in Orion, actually, I'm lying. Actually, Rigel, which is known as the second brightest star in Orion, is actually the brightest star in Orion, which is kind of interesting overall. And that's because Rigel gives off a lot of ultraviolet energy as well that Betelgeuse does not. But that's another topic for another time.
Can I jump in there?
I mean, sure.
I learned recently that the star Safe in Rigel, which is at the lower left-hand corner opposite Rigel at the lower right-hand corner, Safe is actually brighter than Rigel. Safe is safe. No, in UV. Safe is so hot.
Yeah, you're right.
Safe is so hot on the black body spectrum that it's putting out most of its energy in ultraviolet. So it looks dimmer than Rigel, but it's actually brighter.
Yeah, tens of thousands of times like the sun, and these are, and that's what we're gonna be talking about, these different stars in Orion tonight as well. So we'll be getting to that, and Daryl will have, I'm sure, a lot to add to it because he's really good about these things. He knows these things, which is really, really wonderful.
Oh, I'll talk your ear off.
Oh, I know you have, and that's kind of why you're here, because I absolutely love it when you share with with people your knowledge, okay? Because your point of view and my point of view are different, but they're the varied opinions give a nice rich assortment of things to listen to, and people can actually figure things out from how we both say it. And then Amanda comes in, says something, and people are saying, hey, that's a question I was going to answer. So I think the chemistry is good. We have this chemistry of Amanda asking the questions people are trying to formulate in their own minds. Then you come in and backfill other things. I mean, it's a good combination. I really like it.
Everything's better with Amanda.
Thank you.
And
besides,
Daryl told me that earlier too, by the way, folks.
Besides asking questions, I also remind people about breaks coming up.
Yeah, you do. We have one. It's like we're about 2 minutes away, I think.
No, I think it's time now.
Really? I don't hear. How nice. All right. Well, you know what, folks? We will return in just a few minutes after these words from our sponsors. And thank you for joining us on Sky Tour Radio. We'll be right back.
Do you want to lose weight but have no idea where to begin? The Fast Start Diet, a 3-day weight loss plan, is the answer. 3 days of nutrition.
Fulfills its slogan perfectly. The tea that makes you go. So if you want to be on your health game, log on to getthetea.com and order life-change super strength tea. Packages come in a 1-month supply, and when you brew this stuff, wait until you see the results. Aren't we all about the results? With a lot of people's health struggling, we can use a little bit of help. Doctors will tell you disease starts in the gut. So log on to getthetea.com. That's getthetea.com. Be our next email saying, I love this tea. I mean, I love this tea. Get the tea at getthetea.com. Helping America one tea bag at a time.
When you're always on the go, it can be a hassle getting the proper servings of veggies and fruits into your everyday diet. Life gets hectic, making it hard for us to always make healthy food choices. Not to mention it's pretty expensive. Wouldn't it be great to ditch the long grocery store lines but still get your fruits and veggies all at once? What you need is balance of nature fruits and veggies. Made with 34 of the highest quality fruits and vegetables in the globe, right here in the USA. Balance of nature is 100% natural, organic, and was only for a limited time. Use discount code TOM and you'll get 35% off your first full set of balance of nature and veggie capsules along with free shipping. Call 1-800-246-8751 today. Ready for the real results you want and need? Then you need balance of nature. Call 1-800-246-8751. That's 1-800-246-8751 and use code TOM.
Mainstream media's most modern. KGRAradio.com.
Hey there, welcome back to Skyter Radio. I'm Mark D'Antonio with my special co-host Amanda Curran and our wonderful return guest Daryl Mason. So we were talking before the break about a whole bunch of stuff about the Orion Nebula, which we mentioned about how the emission works with the Orion Nebula, that red color. But the Orion Nebula is not just red; it's also blue. And so what's that? Well, also in space, what happens is when a star loses its outer envelope, like happens with these large stars sometimes, many times those gases and so forth, they combine, they form molecules, and these molecules form dust grains, and these dust grains are all throughout the universe. So we see a lot of dark dust, and when you look in the Orion Nebula, you see dark dust. If you look at it with a Skyter live stream, you will see a lot of this dark dust, which is silhouetted against the brighter nebulas behind it, and it's really beautiful. But this dark dust is actually the place that, it's from whence the planets come when those combine, and as we were talking about the latest research, that there were 10 times as many substellar objects than previously thought in the Orion Nebula. Stuff formed from this dust and so forth. Now, things from gas include the brown dwarfs, which we talked about earlier. Daryl characterized them as failed stars. That's essentially what they are, right? They're very hot, but not hot enough to form or to cause nuclear fusion, all right? And fusion, of course, is when we say the star ignites, okay? And that's kind of what Daryl was referring to there. But there's also a lot of planets that have been formed. But planets, are you ready for this? Planets that aren't tied to any particular star system. In other words, they're rogues. They're just they're planets formed out in the middle of the nebula somewhere, and there's no star to which they can orbit. So that means that these will be cold, dead worlds for evermore, unless for some reason they get captured by a star and end up evolving over billions of years into something more. So that could be another possibility that are happening in the Orion Nebula. That's also happening. Now, also among these substellar objects in the Orion Nebula, as it turns out, there's a rich assortment of these small, low-mass red dwarf stars. Now, remember, Daryl mentioned something earlier. He said that, and this is something that is true, if the brown dwarf was to gain more mass and become a star, they would probably have to be about 80 times the mass of Jupiter to form a star. That star is going to be a low-mass red dwarf star. Well, guess what? We're seeing that there's a rich assortment of these low-mass red stars in the Orion Nebula. So could it be that the brown dwarfs either amassed more mass and became red dwarfs, or were stars originally that formed from having just enough mass to form a star and became the red dwarf. It's all a strong possibility. Amanda asked the question about whether a brown dwarf could get more mass somehow. It's possible. It's possible, depending on the situation and the environment that it sits within. But if you think about it, that's kind of a really interesting question, isn't it? So I would say that we're talking about a really fascinating location. And this is just one of millions of nebulae that are in the galaxy overall. One of millions. So we're talking about one little spot. And it's just so cool. So we could also find that there will be planets around that are not tied to a star system, as I said, but we'd also find that maybe some are. And planets could be around a nice young star that's forming within the Orion Nebula. We know this is happening as well. So the other thing that's interesting is that stars that are cool like that, like the red dwarfs, and they're cool, thumbs up, but they're also cool as in temperature. But stars that are cool in temperature also, believe it or not, can have water vapor molecules in their stellar atmosphere. Water vapor molecules. Now that means the temperature has to be pretty darn low to allow the formation of water vapor molecules, but we've seen them. So clearly, this is an indicator that water is ever present throughout the universe. Water is from whence we came. We were in the oceans at one point, and we evolved out of the ocean, and we took a little bit of the ocean with us, and we encased it in something called the skin. We are salty, and that salinity that we have is but a third of the ocean salinity, but it's a salinity nonetheless that's based on the fact that we have a little vestigial ocean within our skin that we cart around like a strange turtle. And that water helps us survive. Without it, we wouldn't. So it's kind of a really interesting evolutionary trait, an evolutionary characteristic of the human species. Very cool stuff, And we've talked about how we've evolved on this planet. And evolution on our planet is a specific chain, probably very specific to us. We've had 5 major extinction events on the planet, 2 of which were probably changes in the biodiversity, which is something that is very possible. And the less diverse forms of life at some point, that conduit can narrow sometimes. And we have very few, diverse life forms. And those are read as an extinction event in the fossil record because we don't see very many life forms at that point. But we've had some major impacts on the planet, too, that have caused extinctions. There's been 5 major extinction events, all right? And so that colors and changes the way life will develop on our planet. So we actually had, back in the Permian era, 252 million years ago, we've talked about this on SkyTour Radio and in SkyTour Livestream, 252 million years ago, the Permian extinction event was one that wiped out the dominant species at the time on the Earth. And it was actually the precursors to mammals that were hardest hit. So mammals, or their precursors, were actually the dominant life form back then. So you see that given its own development, a planet will tend to choose a mammalian life form for its dominance, at least here. We don't know how it'll act elsewhere, but at least here, given the same conditions, mammals want to be dominant. But the extinction events wiped out a lot of the mammals' niches and made it hard for mammals to survive. So therefore, the mammals were left to hide in the shadows, and the reptiles came to the forefront. And thus began the age of the reptiles, which lasted until the Cretaceous-Paleogene boundary, that is 65 million years ago, when the asteroid struck off the Yucatan, and once again changed the entire fabric of evolution on this planet, ultimately and irrevocably. And it wiped out the big reptiles over time. It took several million years for the overall effects to be felt throughout the record and throughout history. But when it did, mammals were no longer going to hide in the shadows. They could actually come and they rose to become the dominant species once again. So what's it tell you? It tells you that on planets where you have a planet in the habitable zone, like our planet orbiting the sun at the not too hot, not too cold location, and where you have extinction events, it seems that mammals always seem to come back. So maybe that's a template in the universe, like we've talked about. It's also a template that we have bilateral symmetry, and that bilateral symmetry is being the same across the center axis of the body. Now, how the layout inside is doesn't matter. How the interface, though, with the world is through a symmetric body. Every life form is symmetric on our planet, every single one of them, every advanced life form. So that could be a template. The universe is telling us something. It's telling us, hey, this life is favored in the universe. So that means that if we find life forms, they're not necessarily going to look like us because their evolutionary record could look a lot different. However, if we find life forms around another star, around another Earth-like planet, well, then maybe they're going to be a life form that's different color, different shape, possibly, but it'll probably be symmetric, bilaterally symmetric across the center. And if so, different as it might be, it may be able to rise to some level of intelligence. We don't know. See? And when we look at the Orion Nebula, we see 10 times the opportunities for this than we ever thought possible. So there's a lot going on throughout the universe that we're just learning, and the fact is it's finds like this, actually, that make us reevaluate how many Earth-like planets might actually be in our galaxy. I read a paper, which I haven't vetted yet for accuracy, but it says there could be up to 100 billion Earth-like planets just in our galaxy. Now, we already know there's more planets than stars in the universe based on what we see. It seems that each star that has planets usually has more than one, and we don't recognize that right away until we look at data from continuous forays out to find planets. But it seems like that there's more than one where there are planets around stars. We don't expect to see stars stars that have planets up in the O and B star range. Now, O stars are the hottest and M stars are the coolest. All right. But O and B, very, very high and copious amounts of ultraviolet radiation. That's a sterilizing radiation. And in the Orion Nebula, where planets are forming, there are stars that give off a lot of ultraviolet energy. Why? Because if you look at these stars and you look at the shape of the nebula, you can see that the red areas are areas where ultraviolet energy was absorbed by the electrons in the hydrogen atom, bounced off the atom, and then recombined to give off that characteristic red light we're talking about. Okay, so we know that ultraviolet energy there is very high and probably wouldn't be conducive to life-bearing planets. There might be planets, but maybe not life-bearing. The nebula is just one part. It's the parts we don't see that are the magical places. Within the dark nebulae that are there, the dark nebulas, well, these are areas where the ultraviolet energy may not be. It only has a certain range. It drops off as the square of the distance from its source. So it'll rapidly end up dropping off to the point where its energy no longer is hot enough and intense enough to ionize these atoms. And who knows? Maybe that's a point where when a planet forms, life can be in existence on that planet. See? So this is very interesting. Now, if we also look at the Orion Nebula, we kind of know where that region is. We actually see very sharp delineations between where the red hydrogen alpha regions, that is the ionized hydrogen is, and where the blue areas are, which is just reflection nebulae. Now, there's still hydrogen gas there. So why isn't it ionized like the red parts? Well, it's not ionized. First of all, it's not distributed evenly. It's a rather of a hodgepodge of a distribution of hydrogen. But in the areas where there's hydrogen that isn't ionized in the nebula, it's not ionized because the stars are hot and they're blue, but they're not close enough to this hydrogen gas to ionize it. But they are close enough to the dust in the nebula to have the dust reflect its starlight. And that is what we call a reflection nebula by that very name. And these are blue. The most famous ones that you are familiar with are just toward the west at night, just after sunset. And if you look up, you see the Pleiades, which is the seven sisters. It's a very tiny little grouping of stars in Taurus the Bull, and they are known as an asterism. It looks like a little shape of a tiny little dipper, right? And this is the Pleiades, okay? And the seven sisters. And those stars are traveling together. They're hot B-type stars. They do give off a lot of ultraviolet radiation. However, they're traveling through an area of the interstellar medium where there's a lot of dust, but not much hydrogen. So we don't see hydrogen emission from the Pleiades, but we see lots of reflection nebula from the Pleiades. If you take a long, deep sky shot, in fact, on my screen right now, I'm seeing the reflection nebula of the Pleiades that we've taken in the SkyTour live stream. And the SkyTour live stream shows that beautiful reflection nebula. Daryl's a big fan of this. He loves there's one star within the Pleiades called Merope, and there's a beautiful nebula associated with it. Looks like it's combed, like a combed appearance, and we've captured that beautifully in SkyTour live stream. But to take an ordinary photo of the Pleiades, you just see these stars. You don't see the nebula. You have to do a deeper photograph for a long period of time to actually check it out. So it's pretty interesting, you know. So, but let's just, you know, speaking of Orion, let's actually speak more of Orion. We've all seen Orion, but I want to paint you a little picture, okay? Imagine it's a crisp February night. Oh, wait, I don't have to imagine. I have those frigid temperatures tonight, okay? Now, as the sun sets, all right, you see the deep red at the horizon, the western horizon, give way to the purples and blues of the dusky evening. And then in the southeast, you can see one lone star beginning to show up, you know, long before it's dark. Okay. And what you're seeing is what's known as the dog star. It's Sirius, Sirius. And that's the constellation Canis Major, the hunting dog, the great hunting dog, which actually is Orion's hunting dog. And we don't see Orion yet. We just see Sirius when the sky is not quite this dark. And we see this star before all the other stars. And it's in the constellation of Canis Major. And Canis Major is to the left of Orion. And in mythology, Canis Major is one of Orion's hunting dogs. Now, this star easily outshines all the other stars in the sky because it reigns supreme as the brightest star in the entire sky. All right. Now, this isn't because it's a giant star. This isn't because it's this massive ultraviolet light generator. It's not because it's a hyper giant or a massive giant. It's not any of those. It's a regular star, kind of like the sun. It's fusing hydrogen into helium. And it's a star kind of like Vega in the summertime sky. Although it's only 8.6 light years away, Vega's over 25 light years away. But because Sirius is so close at this 8.6 light years, it looks so bright in our sky. Alpha Centauri is the closest star, 4.3 light years. But it's a G-type star, and it's a pair of actually G-type stars with a smaller red dwarf circling both of them. And it's not quite as bright as Sirius. All right. So this is the same, like I said, rough spectral type as Vega. Although Sirius actually has a companion star that's orbiting it that someday we'll talk about, because there's a theory out there that ancient peoples knew about this companion star long before the possibility of seeing it was ever manifested. But I think that's, you remember that, the Dogon. I think that's actually a mistake in mythology or a mistake in the cultural understanding. But you know what? I have an open mind about it, and so we'll research it at some point and talk about it on the show. Now, as it gets a little darker in the evening, we see now not just Sirius, but we actually start to see Orion showing up. And usually you'll see Rigel at the lower right. Remember, Orion is a rectangular outline of 4 stars, and then in the middle there's a belt of 3, right? Everyone knows Orion. So as it gets a little darker, you'll see the characteristic shape of Orion showing up. All the stars are around nearly as bright as each other. Saiph doesn't appear as bright to the eye, and Bellatrix is less bright to the eye than Betelgeuse upper left, and Rigel at the lower right. Saiph is at the lower left, and Bellatrix is at the upper right in the square. And then the 3 stars in the middle are Alnitak, Alnilam, and Mintaka in order, left to right. And those stars, those 7 stars, actually form the basis of Orion for most people. All right. Now, if we look at those stars, we actually see that there's a lot more going on. All right. And we see that if we look at, say, as it gets a little bit darker, we start to see this outline. We'll also notice something else below the belt of 3 stars. You'll see that there's something else down there, this little fuzzy thing. And it looks like a vertical set of stars. There's like some stars and then a fuzzy thing and a few more stars below that. Well, that's the vertical dagger on Orion's belt in mythology. And actually that vertical dagger, I should say, is made up of stars that comprise a nebula that's a reflection nebula, as well as a mission called the Running Man Nebula. And below that, we have the Orion Nebula. The Orion Nebula is the most famous naked eye nebula that you can see. And the fact is, you can see it with your eye. And there's a reason you can see it, which we're going to talk about shortly. And it's a very famous star-forming region, like we've talked about. So Orion and its stars are bright, and they're relatively close to us, considering these absolutely astronomical distances. But the question I want to bring up with you is, why is Orion so bright? And before we answer that, I would like to see if there's questions from the chat that people might want to have answered. So Amanda, take it away and let me know if we've got something out there. I want to try and give everybody a chance to participate tonight.
Well, actually, you touched on one point a little bit. You didn't really go in depth. Eric wanted to know if you could touch a little bit on the Orion connection with ancient Egypt. You said something about the mythology. They may have gotten it wrong, and that they could talk about things that they might not have been able to see.
Oh yeah, I was talking about the star Sirius. Because Sirius has a small companion star that you can't see without a telescope. So how the Dogon, D-O-G-O-N, tribe know, or it's suspected they knew, based on their writings, their what they left for historical record, that they knew about what's called Sirius B. Okay, Sirius A is the bright star we see in the sky. Sirius B is the little tiny companion that circles Sirius. Now, one thing I thought was, is it possible that at the time of the Dogon, is it possible that maybe at the time of the Dogon, Sirius B was actually a larger star, and that it evolved catastrophically to something else?
May I jump in there?
But it turns out that's let me just say this: it turns out that's probably not necessarily true. But go ahead, Daryl. We've got about 3 minutes left.
Okay. The ancient classical civilizations often described Sirius as ruddy, R-U-D-D-Y, ruddy, meaning red.
Yeah.
When we see it nowadays, obviously it's a blue-white star, but it twinkles really prettily, especially around Christmas. And yeah, as you said, some would speculate that Sirius B underwent some catastrophic change in the past, like, going to the white dwarf stage, which I guess it is now, whether it might have thrown off a planetary nebula or something that gave Sirius a reddish hue.
Yeah.
But current, astronomical theory says that's not possible in that time frame, that if they saw that thousands of years ago, we'd still see it now.
Yeah,
obviously
we'd
we
see
don't.
a planetary nebula, but we don't even see that.
Right.
Yeah. So that's a very interesting thing. And what Daryl's saying is true. I think it's really interesting because I'm very I'm mystified how our history is replete with some of these accounts, yet we can't show anything for it. We can't really figure it out. Chinese astronomers in 1054 AD did see something in the sky. It was a star as bright as in the daytime and at night it was actually not visible to the Chinese, but during the day, you could see it during the day through blue sky. It turned out that was a location where a star had exploded. And we found that star. That's called the Crab Nebula. And we see that remnant. So we want to find evidence for some of these assertions like Sirius B. But, we'll talk about more of that. And we're going to talk about why Orion is so bright when we return after these words here on Sky Tour Radio. I'm Mark Antonio here with Amanda and Daryl. We'll return in a moment. Who seems to be returning a lot. I think that we should make a place for him permanently. What do you think, Amanda?
I would love it.
Yeah, we gotta leave
Of course, he makes the final decision, but that's my 2 cents.
Yeah, we'll leave it in Daryl's court. But,
we'll see.
There you go. See, we're not going to force Daryl to do anything because Daryl, he's a font of knowledge, and I just think that he's fun to have on the show.
Me too.
So I would like to ask, though, you had a comment or say something in the chat room, Amanda, that might be worthy of talking about now before we talk about why the Orion stars are so bright.
Yeah, well, with the questions coming in, Laura Lee wanted to know is Orion a preferred area for exploration and or imaging by NASA? And I thought that would be a wonderful lead into our next portion.
Oh, that's a very good question.
I told her that Orion is it. Orion has it all. I mean, it's got everything you'd ever want to look at. She used the word anomalies. I wasn't sure what she meant by that, so I just said cool stuff. But Orion has it all. You can't beat it.
I agree. And here's the thing about Orion, and this relates to Orion's placement in our galaxy and our placement relative to Orion. And here's really how it works. Our sun is a certain distance from the center of our galaxy, and Orion is also a certain distance. It turns out that those distances are nearly the same. We are in what is called the Orion arm of our galaxy, and to discuss that properly, I'm going to take you through the different types of spiral arms and what we thought of what the galaxy looked like in the past versus what we know it looks like now, and so forth. I do want to do that because that's really important, I think, to understand why we see what we see. Right, so we know that galaxies have spiral arms. And what are these spiral arms? Spiral arms are places in galaxies where stars form. And usually we see a central bulge in the galaxy and then a disk out from that bulge, obviously in all directions, a disk in all directions. And within that disk, we have concentrations of stars that form spiral arms that seem to wind out from the center and go around the galaxy, sometimes almost a full turn around. And these spiral arms and their origins have been a mystery for a long time. We can talk sometime in the future about how spiral arms form around galaxies. There's a number of theories. One of the theories has to do with something called a density wave. And kind of like it's kind of like traffic on a highway. You can go up on a highway, drive along, and then all of a sudden you reach a slowdown, a traffic jam. You get through the traffic jam and keep going on your way in your car. Well, you're a star. If you're a star, that traffic jam is still behind you, right? And all the stars or cars moving through that traffic jam are still in the bunch up, and then they come out of the bunch up, but they get through it. They're not moving together with the bunch, with that traffic jam. They move through the traffic jam, but that traffic jam from the air is still there, but it's always different cars. In the same way, a spiral arm in a galaxy has different stars moving through it. And there's always that traffic jam is the knottiness, that compressed area of the spiral arm, but the stars move through it. So the traffic jam analogy is the best way to think about how spiral arms work. But we're inside our galaxy, and we can see other galaxies from within. And when we look at other galaxies, we can certainly see that they have these spiral arms. All right. Some galaxies look very different from ours. All right. And trying to figure out what we look like from inside is a bit of a chore, as we'll see. But our galaxy is different from what we imagined. Now, our galaxy, we thought, now we've talked about this before, we thought our galaxy was a regular spiral galaxy for many years. Now, if you remember, we did a Sky Tour radio way earlier in the beginning that talked about classifying galaxies by their shape and their spiral nature if they had it. And the spiral nature was either a tight spiral or kind of an unwound looking, unkempt spiral. And those were different classes of spiral galaxy. And it was Edwin Hubble, a famous astronomer, who actually classified galaxies by this shape and by their structure. And his results became known as what's called the tuning fork diagram. And galaxies were either a spiral or they were an elliptical galaxy that didn't have any spiral arm structure at all, but just looked like oblate elliptical collections. And then there were others that were called barred spirals. These were spirals like regular spirals, except the nucleus wasn't round. It was elongated. It had what's called a central bar of stars. Well, we thought that we were kind of one of these regular spirals, okay? And let's go back to the beginning of the tuning fork diagram. The tightest elliptical galaxy would be a semi-round ball of stars. All right, I mean billions of stars, and some of these galaxies are the biggest galaxies in the universe. And it was designated E0, elliptical 0, and it went down to E7, okay, and it was in more and more oblate nature. So in E3 was oblate, and E7 was even more oblate. But then we got to where some of these seemed to show that they had spiral structure, although it was very tight, extremely tight spiral structure. And this became the base form of the spiral, and that was the S0. All right. Now the S0 had these very tight spiral arms, almost looked like an elliptical, but it was very, very tight spiral arms. Now, this is where the tuning fork splits, because if the next galaxy you looked at had this round nucleus and then less tight spiral arms, but still spiral arms, then it was called an SA, capital S, little a. All right. Less wound, other than beyond that, was an SB, and then SC. For instance, those that know the Triangulum galaxy, we're looking at an SC galaxy. Those that know the Andromeda galaxy, we're looking at an SB galaxy. All right. And then the other end of the tuning fork diagram, we thought we were an SB. At one point, we thought we were an SA, and then we thought we were an SB. And then the other end of the tuning fork now goes from that S0 again, not up to an SA, SB, SC, but down to something called a capital S, capital B, little a, SBA. What's that? SBA is barred spiral, but the tightest form. And that means an elongated nucleus. And then the next one was a less tightly wound barred spiral. And as you can guess, it's going to be the SBB. And then the SBC for the least tightly wound. Okay. And it turns out that we're not an SB, that is a spiral galaxy of moderately tightly wound arms. We're an SBB. We're a barred spiral. We have an elongated bar in the middle of our galaxy. Now, I think that's interesting that, and Amanda's going to share the image of this tuning fork diagram in chat if she hasn't done it already.
I have.
And she's right on the ball as usual, folks.
And I was following along.
No, she's good. She's good. So, as you can see, we think of ourselves now as being an SBB. All right. So that's a major change to what we thought we were. All right. So we have this extended bar of stars that make the nucleus of our galaxy more like a lozenge shape, a longer shape, with spiral arms off of that. Now, it's no surprise that's really hard to see, as I mentioned, from inside. When we look at other galaxies from the outside, we can see their shape. Oh, yeah, that's a barred spiral. Oh, that's a regular spiral. Yeah. But, it's like being, opening your eyes and you're in a forest, looking around, and you're unable to move around. So you got to look at it like from the perspective of the tree you're tied to, okay? And then you're being asked to describe the entire forest beyond the most distant trees you can see. Well, how do you get that right? At some point, the tree's blocked looking any further. Another way to look at that is if you're mapping the spiral arms, it's like trying to figure out how the entire house looks from the outside while being confined to one room, So that's basically what we've been up against, trying to, look at our own galaxy from inside. But we have discovered that now that we know we're a barred spiral, we know that we have 4 prominent spiral arms, okay? And those spiral arms are the Scutum Centaurus arm, okay? That's mostly a southern hemisphere object from our position in the galaxy as we're rotating around it. And so that's seen mostly from below the equator, and it's in the southern sky. And the same goes for the Norma arm, which is also pretty much the southern sky. But then extending northward and southward is the Sagittarius arm of the galaxy. And that's looking kind of toward the galactic center from our position at the sun. And, at the center of our galaxy, we think we have a massive black hole there, and we call that Sagittarius A. And so I guess, see, black holes can absorb more objects and become larger in mass, and so they're going to grow in size. There's a calculation you can do to figure out the size of a black hole based on its mass. You can't, for instance, have a black hole that's the, size of a millimeter and have it hold, the mass of, Betelgeuse. Okay. There's a certain size associated with the mass. So then moving outward, there's actually it's a minor arm. It's called the Orion Cygnus arm. Now, Orion is a winter constellation, and Cygnus is a summer constellation. But they're in the same galactic arm. And it takes moving around the sun for us to be able to see that whole arm a little more clearly. But we do see the Cygnus arm. When you look at Cygnus overhead, you can see the Milky Way. If you're in a dark site, you can see the Milky Way over your head. And believe it or not, you can see the Milky Way in Orion too, if you're in a dark spot, because there's a plethora of stars in Orion. All right. So when if we're looking at Orion, we're actually looking about 90 degrees away from the center of our galaxy. So not all the way around, but just part way around, halfway, 90 degrees away from the center about. And we are part of the Orion arm segment of this overall arm. Now, that's formerly been known as the Orion Spur, the location in our galaxy where the sun is. But this is why the stars of Orion are so bright, is because we are right there with them. We're almost like in the same spot, effectively, So I think it's kind of important to kind of know our 3D placement. All right. Then looking farther out still, turning further away, where we now have the center of the galaxy behind our heads, we're looking out at the Perseus arm for the most part. So where we have Cassiopeia and Perseus, and that beautiful double cluster that we often take photos of in Sky Tour live stream, we're looking almost directly away from the center of our galaxy. All right. And you know that you are, because overall, in a dark sky setting, you can see that we're seeing overall less stars than if we look toward the center of our galaxy, as we're looking toward the outside. And our location is actually very interesting. And this is something that we have not discussed. Okay, our zone where we are located is in a place called the Galactic Habitability Zone. Now, it's a little controversial, but the concept is interesting. The Galactic Habitability Zone, the GHZ, depends on having stars that are conducive to planet building and stars that are conducive to long lives without catastrophic disaster. And basically, stars that are conducive to planet building means that we have stars and abundant raw materials from which to make planet when a star is forming. When we formed from something called the solar, and the solar nebula was full of elements created in other stars elsewhere. And then they ended up forming planets here with all the materials made in these other stars. So when Carl Sagan famously said, "We are made of star stuff," it's absolutely true. Every element, every atom in your body was once forged in the heart of a star. If you think about that, that's an amazing thought. And to think that the universe is that vast and that amazing of a place, that time is such that we can actually wait around, or life can wait around to come about based on all the many things that we see forming in the universe. That just astonishes me. So we call the availability of these materials, that depends on something called the metallicity, metal-like nature of stars. Now, what does that mean? It means anything other than hydrogen and helium to us astronomers. Okay, we don't think of carbon as a metal. We don't think of neon as a metal. Okay, we don't think of magnesium. Well, we think of magnesium as a metal, but we don't think of phosphorus as a metal. Okay, but anything other than hydrogen and helium is a metal to an astronomer. So that means that these additional abundant elements provide the raw materials from which planets can be made. And the galactic habitability zone depends on that. The galactic habitability zone also depends on there being less catastrophic events occurring in the local area. Things like supernovae or gamma ray bursts. Now, if a star went supernova and left behind a pulsar, okay, which can happen, the pulsar can emanate these high energy X-rays as it swings around like a lighthouse beacon, and those could sweep across a young planet, rendering it lifeless and sterile if it's, you know, close enough. And I don't mean in the same system. It can be a couple light years away. But if it bathes the planet with every, turn with this deadly X-ray radiation, well, then it could spell disaster for a planet. See, so that kind of thing is a very strong possibility, you know. So luckily, we don't have that. We're not within, spitting distance, say, of these stars that can do this disastrous stuff to us. All right, there's no star close enough to us that can go supernova that could destroy us. Let's put it that way. There are stars that if they go supernova, they could damage our ecosystem in some way, but there's nothing that is imminent nor in the far future even yet. But as we move around the galaxy, other stars come near us and go farther. Okay, so that could change. But for the near future, meaning the next 10, 10 to 100 million years, nothing for us to worry about. And there's nothing on the horizon. Now, there was a question when we spoke about stars providing these raw materials. There's something about the collisions that are important to understand. And we're going to talk about collisions in terms of stellar, gas and dust moving outward from a supernova, colliding with other stuff in interstellar medium to spark more star formation. However, that's like I said, the galactic habitability zone depends on there being a fairly stable location in the galaxy. All right. And overall, life could arise in the galactic habitability zone and be given a long time to succeed. All right. And the galactic habitability zone is specified as in our galaxy as being a ring starting from near the galactic center and moving outward in a band that's about 10 kiloparsecs wide. Now, wait, what's a kiloparsec? What are you talking about, Mark? A kiloparsec, kilo means 1,000. So 1,000 parsecs. But wait a minute, what's a parsec? Why are you throwing all this stuff at us, Mark? Well, when we talk about a distance in light years, it can actually get pretty cumbersome, believe it or not. And light years are the scale that we're used to talking about, right? But a parsec is 3.26 light years. Now, I won't describe how we know that, but it's parsec stands for parallax second, and we'll talk about that another time. Understand that it's a distance of 3.26 light years. Now, the scales of the universe are so vast that even light years become too cumbersome sometimes. So the galactic habitability zone we talk about in terms of these kiloparsecs, but let's talk about it in terms of light years, just to put it into something we do kind of understand. The GHZ, this galactic habitability zone, extends from roughly the center of the galaxy out to about 32,600 light years from the center. Now, the galaxy is anywhere from 100,000 light years across to 200,000 light years across. We don't even know. We don't even know the size of our own galaxy, for crying out loud. And that's obviously because we're in it. All right. But Earth is 26,000 light years from the center. So we're within the galactic habitability zone. And that number actually is going to change, actually, because we think, based on some of the recent developments, that we might actually have miscalculated. And I don't mean in SkyTour Livestream or on SkyTour Radio. I mean in astronomy. We may have miscalculated where our Earth is. We might actually be closer to the galactic center, even more within the galactic habitability zone than we thought. So it's very interesting. Now, Amanda, I know there's some questions in the chat, and I'd like to give you an opportunity to pose those for our listeners to hear. So I'm going to turn it over to you now to just go through these because I know that there's a lot to talk about.
Okay, well, I'm not sure if this is kind of exactly what you were just discussing or not. Bill had a question. He wanted to know, I guess it was just recently in the news. This is for both of you, actually, you too, Daryl. He wants to know if you guys can speak about the Milky Way collision with the Magellanic Clouds and the eventual collision between Andromeda 4.5 billion years from now, and how it may affect our solar system.
I
know you were kind of touching on that, so
yeah. Well, see, collisions can cause a lot of things to happen, and as the Andromeda Galaxy approaches, that's something that will be a game changer, but it's not going to spell death and destruction for us. We won't even notice it. The sky will just change over a few million years, and that's about it. That's all we're going to see change. All right. We're not going to suddenly be whipped out of the galaxy and, we're being torn apart. That's not going to happen. Okay. Galaxy collisions move at the fantastical speed of, so we're not going to see any disaster. I'll let Daryl proceed and say what he'd like to say about it. And then I can add some more stuff about the Magellanic Clouds. But go ahead.
Well, it's typically said that you will see practically zero stars collide when Andromeda and the Milky Way come together. They will just pass right through each other. I posted a picture, Amanda posted for me a picture of the antenna galaxies, though, which are two galaxies in active collision, or at least they were at the time, look back time. Gravity may have a huge effect that it can so distort the two galaxies that you've probably seen the animations. It flings stars out into the outer parts of the galaxy or clean out of the system sometimes.
Mm-hmm.
Ultimately, who knows? I mean, it's 4.5 billion years from now, so I doubt I'll be here to see it. Maybe you will be.
If I can use my body, and come back.
We'll be cyborgs if we're still around by then. The Magellanic Clouds, I've heard some things recently that they're not just satellite dwarf galaxies of our Milky Way, that they're capable of or have in the past, which I would not be surprised about if they had literally collided with the Milky Way.
Yeah.
If you look at the Large Magellanic Cloud in particular, there is a ton of nebula and star formation going on in the Large Magellanic Cloud.
Right.
The Tarantula Nebula, I've mentioned before on your live stream that getting back to Orion, perhaps, if the Carina Nebula in the Large Magellanic Cloud was as close as the Orion Nebula is to us, about 1,600 light years, the Carina Nebula would fill half our sky. It would be just huge, tremendous.
Yeah.
All over the place.
Here's something interesting. Large Magellanic Cloud. First of all, why are they called that? Where are they located? We've never seen them in the northern hemisphere. They are in the southern hemisphere. First seen by Ferdinand Magellan, documented by Magellan as he circumnavigated the globe. And now we know that they have been called companion galaxies to our own. Not necessarily the case anymore. They may not be gravitationally bound to us at all, in fact. That's some of the latest research, but we have to vet that. There's more research to be done. But it's interesting because we look at the Magellanic Cloud. There's a large and small. The large one has an awful lot of star-forming regions in it. And as Daryl just said, the Carina Nebula within the cloud has this massive amount of hydrogen ionization going on. So something caused this starburst formation to go on there. And it could very well have been that it's already made a close pass through our galaxy. We don't see that yet, but it's possible. In any case, that I find to be just fascinating. And we're going to talk about that some more probably in future shows. We may actually do a future show on the large and small Magellanic Clouds, even though I've never seen them in my life.
Me neither.
Yeah, see, we're northern hemisphere, folks. We don't get to the southern hemisphere. Australia is on the bucket list, though. I've never been there. I really want to visit Uluru, which is Ayers Rock. I want to visit Siding Springs Observatory down in Australia. I want to talk to astronomers there. And I just want to hang out. I actually belong to an observatory that was set up down there, and I could log in and take photos. But that observatory ended up getting closed down, unfortunately. So we lost the opportunity. But I've got photos I took of the Orion Nebula, but I've never seen it with my eyes. So it's kind of crazy. Now, when we come back, we're going to go to our last break of the evening. When we come back, we're going to actually talk about the main stars within Orion. And I'm sure Daryl will have plenty to say, and Amanda will have plenty of questions, which is great. And pardon us if we haven't got to all your questions, but we'll get there, I promise. We're going to work it out. But we will be right back here on Sky Tour Radio. I'm Mark Antonio with Amanda Curran and Daryl Mason. So we'll turn it over to you, our wonderful and esteemed producer, Bill. Thank you. See you. first stars we're going to talk about is what has been classically labeled as Alpha Orionis, the brightest star in Orion. Rigel is arguably brighter, but for whatever reason, Betelgeuse has been given the honors of being Alpha. Betelgeuse is a strange bird. Betelgeuse is actually a very large star. It's a supergiant, and it's the Alpha Orionis. Okay, we give these stars the designation based on Greek letters, alpha being the brightest, beta being the second brightest, etc. So it's like alpha, beta, gamma, delta, epsilon, zeta, eta, theta, iota, kappa, mu, nu, phi, rho, pi, psi. Darn it, I know the whole Greek alphabet, but I'm just looking at 12 things at the same time, so I couldn't get it through. But we start with the Greek letters. So Alpha Orionis is Betelgeuse, and the star is 492 light years away, basically, and it has a spectral type. And I say spectral type as opposed to spectral class. I'm going to define that for you. We've talked about this before. The spectral class of the star is M1 or M2, and the spectral type, all right, is adding the luminosity class, or what type of M star is it? Is it a tiny little dwarf? Is it a big giant supergiant? You add a luminosity class, and you end up getting a spectral type. You get the color or the designation, the letter designation, which gives us the spectral class, and then you get the letter designation for the luminosity class. And together, the spectral class plus the luminosity class gives the spectral type of a star. And we'll make that clearer. We had a show on this, but you know what? I can't expect everybody to remember that. Anyway, so Betelgeuse is an M1 or M2, and that's the spectral class, and its luminosity class is Roman numeral 1 and little b. Now, to understand these classes, I'll have Amanda put the Hertzsprung-Russell diagram into the chat that you guys can see. And you'll see the little 1A, 1B across the top. This is the realm of the supergiants, and these are the stars that are no longer fusing hydrogen into helium. They are way past that. They have grown in size as they fuse other elements in their cores and in shells around the core. And these stars become the largest stars that we have in the universe over, various different types. There's many different types of supergiants, and there's many different sizes of supergiants, but they're all basically one particular size, or rather one particular type of star. Now, remember that spectral type of the star, again, and like I said, is made up of that spectral class and the luminosity class. Now, Amanda is very well versed in the spectral class of a star, and she can tell you all of that. And I'm sure that I can just say to her, Amanda, give us the spectral classes, and she can tell us. Can't you, Amanda?
I can. It's OBAFGKM.
That's right. And it's in order of what to what?
From biggest, bluest, and hottest to smallest, coolest, and reddest.
Absolutely incredible. You see, Daryl, she does understand it. She gets the stuff. And I'm very proud of her for knowing this. She's really good.
I like that question.
She just likes to kiss guys. I know.
That was her little mnemonic for this. That I was taught this when I was actually getting my degree in astronomy. We actually were told that it stands for "Oh, be a fine girl, kiss me."
Or a guy, depending on your preference.
That's what I was taught.
There you go.
Well, as you were taught, yeah. And I am proof that it actually works. So you told me that about a year ago, and I don't think you've ever forgotten yet.
No, in fact, there was a time where you would actually go through the letters, or rather the phrase, the mnemonic in your head, and then you'd come out O-B-A. She's saying O-B-A, fine. She's going through it.
Because the first little bit works, because O-B-A, O-B-A, it works. And then it's just fine guy kiss me is FGKM. And you can still hear the little break. I do still go with the pattern of the words, but it works. And I also remember there used to be an S after that for smack. I hope you fine guy kiss me smack. No? Did we lose Mark?
We may have lost Mark. I'll try to get him back so you guys continue
I'm
on.
here. I haven't
Okay.
lost- I don't know what
Oh,
happened there.
couldn't hear you for a second there. Okay.
No worries. Okay, no, I said there was an R and an N and an S. So
Oh, right now, smack.
right.
Yes.
Yes. Yeah.
See,
So
because I was offended at first. I thought smack was someone getting slapped across the face, but it's not. It's of a
yeah,
kiss.
exactly like a kiss. Yeah.
I
It's
love it.
it's a silly mnemonic, but it's how when you teach people astronomy, it's one of the first things they learn. And it just nowadays the RNS is sort of abandoned. We don't really talk about it that much, and we pretty much stick with the OBAF GKM spectral classes. But really it's important to go down the path of knowing what that means. And you did it right. You said it, the hottest, largest stars down to the coolest, tiniest stars. That's kind of how it goes. So when we talked about Betelgeuse, we talked about it being this spectral type of this M1 or 2, which is supposedly a cool star. And Betelgeuse actually does have a very cool surface, yet it's the largest stars there is. So you say, well, how can that be? Here's how you can be. The redness of the star is dependent on its temperature, right? And temperature hottest to coolest, OBAF GKM to the coolest down at the M's. The outer layers of that star are so far from the energy producing core of the star that they're coolest. They're cooler and they're more red. So even though a star is very, 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 very bright and very, very hot, if it's a large star, those outer layers are far enough away that they are going to be cooler. In fact, in some of these stellar atmospheres, you could actually find that you actually get molecules forming in the stellar atmosphere itself, which is really mind-blowing when you think that a molecule can form there, considering that these molecules are typically dependent on a whole bunch of things, including the fact that you can have a low enough temperature that you can actually end up with a molecule that isn't destroyed by the heat, and the intensity of radiation, right? So that's a spectral class that gives us the color of the star, that OBAF GKM. But then that luminosity class, that Roman numeral that comes after it, that's based on the intrinsic brightness of the star, and it's related to the radius of the star, which itself is related to its evolutionary state. So Betelgeuse, for instance, has finished off fusing hydrogen into helium, and it's now in a state where it is actually fusing other things in its core and in shells around the core, which causes it to bloat up really, really large. And that's the supergiant that is Betelgeuse. Now, if you recall, normal stars that have a luminosity class of the Roman numeral 5 or the V, okay, those are on something called the main sequence. And if you look in that Hertzsprung-Russell diagram that Amanda put up in the chat, which I'm sure is there, okay, that forms something called the main sequence down the diagram from the upper left to the lower right. That's where most normal stars live and exist, right? They're fusing hydrogen into helium in their cores. But once they finish off that hydrogen, then they evolve away from that main sequence. They kind of go up, from wherever they are, they kind of go up and a little bit to the right. And you can actually kind of see that little path going up and to the right there in the middle of that diagram. And they go into the potentially into the giant stage. Certain stars go into the supergiant stage, and there's even stars bigger than that, which are not even displayable on this diagram. They're called hypergiants, and they're stars that are very, very large. I mean, Betelgeuse is no small star. As we talked about, it's definitely a red supergiant. It started making the helium in its core into carbon and so on. And more massive stars continue to fuse all the way to iron in its in their cores, and iron is at number 26 on the periodic table, and that's as far as stars get under these processes of evolution of stars. Then they go to things like supernovae to make some of the other elements. In stars like the sun, we get to that, we called that S process earlier, which is what's called neutron capture. Neutrons end up getting captured into atoms, and they get converted to protons, making heavier elements. Remember, protons make the elements. Neutrons make isotopes of that same element. So converting an isotope to a heavier element means converting a neutron to a proton in an atom. And that does happen in stars like the sun in this process called the S process. Okay, so there's a number of ways in which we get heavier elements. And one of them is this supernova where we will get a number of heavier elements. And so Betelgeuse is a fairly interesting star because you think, well, it's an old red supergiant, isn't it? Actually, it's not old at all. Believe it or not, it has 12 to 17 times the mass of our sun, but it quickly used up the hydrogen in its core and expanded to a red giant. Believe it or not, that star is only 10 million years old. Our sun is 4.6 billion years old, and it's going to live another 5 billion years or so. So Betelgeuse is only 10 million years old, and it's already approaching the end of its life because it was so massive to begin with, And it's actually got, if we look at the size of Betelgeuse in the sky, okay, not the actual size of it in reality, but the size of it in the sky, it's the second largest angular diameter of any star in the sky. Betelgeuse has been the subject of many studies, and we have photos of Betelgeuse as a disk. It's one of the very few stars that we can actually see the actual disk of Betelgeuse. Absolutely incredible. And now, again, that size is not related to its size in life. So to say like, well, it's how many, it's 650 times bigger than the sun. If you put it in the center of our solar system, it would extend out past Mars. Well, that relates to the angular diameter only because it's only 492 light years away from us. Okay. Now, take that same star and move it 15,000 light years away, and you'd never see the angular size of it in the sky because it's way too small at that distance. So distance and its overall intrinsic size are why we can actually see it. And we've done that with a few stars, not many. And we've noticed that Betelgeuse has a really strange shape. Okay. And that shape is something that looks kind of lumpy. Its surface has these asymmetric bulges here and there. And what are those? Well, it turns out that our concept of what a red supergiant was is wrong. And those books have been rewritten to include a process for allowing an asymmetric star. That is to say, a star that has lumps all over it that aren't symmetric. We think of stars as round like the sun. Well, how about a star that actually has lumps on it? Kind of like a moldy tomato, with lumps all over it. I mean, big lumps. So if you had a tomato, imagine a lump that's like an inch and a half in diameter sticking off one side of the tomato, and then one elsewhere on the tomato in a very different location sticking off a half an inch, and one at the bottom sticking off another 3/4 of an inch. This is what red giants look like. They're lumpy, and their material goes farther out than its original diameter and then just settles back in. And this is incredible. And we think these lumps are giant convective cells within the outer layers. In stars like Betelgeuse, the outer area, the outer surface, the outer, layers of the star are all convective, like a boiling pot of water. It's all convection going on out there. And when that happens, you get this really lumpy appearance. And if you look up the images of Betelgeuse, you can see what looks like a bad photograph of a round star. But it's not. It's an accurate rendering, the one taken with the Hubble Space Telescope, actually, that shows Betelgeuse with the lumps that it has. Very interesting. And so when we talk about Betelgeuse as a Alpha Orionis, we really understand now that Betelgeuse is a star whose destiny is likely going to be what we call a type 2 supernova. Okay, that means catastrophic core collapse after fusing elements all the way to iron, which is 26 in the periodic table, as I said. Can't do any more. Fusion will shut down, and gravity's going to win out because that star is always in what's called hydrostatic equilibrium when it's burning normally, when it's fusing normally. The radiation pressure pushing out balances the gravity trying to crush the star back in. And that place it finds itself, that balance point, is that equilibrium point that stars live with for billions of years. All right. And Betelgeuse is reaching the end of that phase. It may have actually already reached the end of that phase. In fact, for all we know, Betelgeuse is no longer there. Maybe it already went supernova. And if it did, then we will end up seeing it once the light train coming from Betelgeuse reaches us with all that information. Right now, we see Betelgeuse as it was 492 years ago, right? For the light that you see instantly tonight, it's 492 years old. But in another 200 years, maybe the light train from the supernova of Betelgeuse will reach us, and we'll see this massive star that appears in our sky. If it happens in the middle of the summer, then it'll be in the daytime sky. If it happens in winter, it'll be in the nighttime sky, and it'll probably outshine the moon easily. Amazing. It'll be like that for some weeks, then it'll dim down, and then astronomers all over the globe will start looking for the remnant of the supernova that was Betelgeuse. And that will start changing the face of Betelgeuse. And so that's Betelgeuse's fate. All right. Now, the next star is Beta Orionis, okay, as it's labeled now. That's Rigel. That's a lower right-hand star in the outer rectangle of Orion. And that's 860 light years away. And it's also a supergiant star. It's a B8 supergiant star. Okay, B8, and then Roman numeral 1, AB. The AB because it's sort of in between the two types of supergiants. You can have a 1A or a 1B. It's a 1AB, so it's sort of in the middle. And it's also a supergiant. And now it has a massive ultraviolet light component too, which is 40,000 times our sun's output. 40,000 times, and that's a heck of a suntan. Okay, that would be instant death, you know. So how about this? If it was the distance of Sirius, all right, Betelgeuse, again, Rigel being 860 light years away, right, as is B8 1AB supergiant, massive ultraviolet light. If it was the distance of Sirius, which is 8.6 light years, it'd be as bright as the first quarter moon in the sky. As bright as the first quarter moon. I mean, that would be a massively bright star. Next to Rigel, the next brightest star is in the summer sky, which is Deneb, and that's the brightest star in the constellation of Cygnus the Swan. All right, and Deneb being a summer constellation, and Rigel, a summer star, and Rigel being a winter star, and being that that's the case, Deneb is 3,200 light years away. And it's further down the Orion arm of the galaxy, and we don't see that until we swing around and get that part of the sky in our nighttime sky as we circle the sun. So there's an awful lot to it. Now, Daryl has a note here about the Witchhead Nebula, which relates to Rigel, and I'd like to let him tell you about it because it's actually a really cool nebula that is near the star Rigel. And Rigel's responsible for illuminating it. So go ahead, Daryl. You can tell people about that if you like.
Hopefully Amanda can post that image. The Witchhead Nebula, to me, looks just like the Wicked Witch of the East or the West, whichever one the green one was, from the Wizard of Oz. It's a striking nebula, if rather dim, but it's very large, and as you said, it's sitting right next to Rigel. That deep exposure Orion I posed earlier, I think it's in there, and it's just really cool looking. You know, the Greeks saw hunters in the sky, and we see witch heads. That's all I really have to say. I just thought people might find that interesting.
Well, it is a very interesting nebula. Now, It's also known by its designation of ICE 2118, and that means index catalog. The index catalog is the actual catalog in which the Witch Head Nebula appears. It's a very large, extremely faint reflection nebula, and that means that the light hitting it is being reflected back to us so we can see it. And it's actually in the constellation of Eridanus, the river, which is a little bit east of Orion. West of Orion. But it's huge. It's pretty big. And like Daryl says, it's illuminated by the bright light from Rigel. And then that light is being reflected back to us. Now, what is it in reality? Well, it's actually a very a very fine cloud of dust grains. Okay, and it's around 900 light years away. Okay, which is good because we see Rigel's distance is relatively similar, and its bluish tinge is actually caused by Rigel's light, in the same way that the Pleiades reflects its blue light to us based on the light Pleiades stars, which are B-type stars. Okay, so I think that it's really interesting to see this, and it's the same. It's kind of interesting to talk about this whole process, but it's interesting to know. We can talk about scattering another time, about how come these nebulas, look the blue that they do. All right, but I do think it's a neat nebula. Daryl's absolutely right, and the Witch Head is a famous sight. Very hard to see because it's faint, but that is. Again, that is the region of Beta Orionis, the second brightest star, supposedly, in Orion. And if you have anything to add, Daryl, you can add now. I mean, I'm going to move on to the next star if you don't want to say anything about it.
Oh, all I'd say is if you want to look for it, as Mark said, it's just immediately to the west of Rigel, I believe. And you would want to park Rigel just outside the field of view in the telescope. The brightness of Orion will overwhelm the nebula. But if you park Rigel outside the field of view of the telescope, you might see the Witch's Head.
Yeah, not bad at all. Now, if we want to go to the next brightest star in Orion, it's Gamma Orionis, and it's called Bellatrix. And this is a star that's at the upper right of the outer rectangle of stars in Orion. And here's what's interesting about Bellatrix. Bellatrix and Betelgeuse and Rigel, and then the lower left star called Saiph, they all look like they're together at the same plane, but they're not, right? Bellatrix is actually the closest star to us in the Orion area. It's actually 240 light years from us, which is not very far, right? It's a spectral class B2 star, so it's an early B, very hot in the UV, okay? It's 6,400 times the sun's luminosity or intrinsic brightness, and it's really got a lot of power, all right? But one thing about this, but it's not a giant that is actually, emanating in the, it's not a giant that's actually done fusing hydrogen. It's fusing its hydrogen, and doing it. So it's actually, it's incredible that it's actually still a normal star, Now, if we move down to the star at the lower left, that's called Saiph, and Saiph, Saiph, okay? Saiph is actually a really cool star. It's Kappa Orionis, the sixth brightest star in Orion. We haven't even talked about the belt, but we're probably going to be out of time before we can talk about the belt stars, but we'll get to them at some point. Saiph is a hot class B1 star, and it's also a bright supergiant that shines with this beautiful bluish white light, and it's actually one of the hotter stars in the constellation. As Daryl mentioned earlier, it's very hot and very emissive in the ultraviolet, making it a very bright star in the ultraviolet realm. Now, the thing about Saiph is that it's actually a star that you see very clearly. It's in the lower left corner of Orion, and it's also something called a variable, and it's eruptive. It does erupt, which is really kind of interesting, and I'm sure that people will be interested in knowing more about it. but it's actually got it's 720 light years away, so consistent with the distance of many of the Orion elements. And so it's about the same as Rigel, but there's a lot going on in that constellation that's amazing. If you want to learn more about Orion, I do encourage you to come to Sky Tour live stream. We have some winter left. We have the winter sky left. We'll be able to look at these in detail and check them out. We will enjoy the properties of them, and we'll talk about them. And we'll go through a variety of, the makeup of these stars and what's been found near these stars. So I do encourage you to join us for that. We'll see SAFE, which is of course a star that's beautiful, like I said, and it's a B0 star, so it's one of the hotter of the B type stars, but it's a 1A, Roman numeral 1A supergiant. So we'll talk about more in the future as we move forward in Sky Tour Radio. I want to thank you for joining us tonight. And on behalf of Daryl and Amanda, I wanted to say thank you for listening. And I hope you had a good time. So remember, folks, keep looking up. And
While you're driving.
Except while you're driving. Thank you, Amanda. I want to thank you both for joining me. And we'll talk to you next week.
Thank
you.